Tycho Brahe and Johannes Kepler were two of the most influential astronomers of the 16th and 17th centuries, and their work laid the ground for modern astronomy. Here's a closer look at the important milestones and background of Tycho Brahe's life. Tycho Brahe was born on December 14, 1546 and died at the age of 54 on October 24, 1601 in France due to either burst bladder or kidney failure. He was taken in by his wealthy, childless uncle Georgian Brahe, who raised him with the intention of providing him an excellent education and training him for a career in politics or law. He studied in the University of Rostock. While studying in Rostock, Tycho got into a duel with another nobleman over a disagreement, allegedly about who is the better mathematician. During the duel, Tycho's nose was severely injured, leading him to wear a metal prosthetic nose, likely made of brass or copper. This incident became one of his defining physical characteristics. Tycho initially studied at the University of Copenhagen, where he was introduced to astronomy during a solar eclipse in 1560. This event sparked his lifelong fascination with the stars. Against his family's wishes, he pursued astronomy, studying further at the universities of Leipzig, Wittenberg, Rostock, and Basel. He also learned various scientific disciplines including mathematics and alchemy.
Let's start with Uraniborg's Urania, Tycho Brahe's famous observatory given him by the King of Denmark. This island became his dedicated research space. Brahe named it after Urania, the muse of astronomy, symbolizing his dedication to studying the stars. Uraniborg was a marvel of its time, equipped with the advanced instruments and tools he needed to make groundbreaking observations. Tycho Brahe is also known for developing the Tychonic system, a model of the solar system that combined two important theories. On the other hand, it used the Copernican idea that planets orbit the Sun, and on the other, it kept the Earth as the stationary center like the Ptolemaic model. This hybrid model balanced both mathematical accuracy and traditional beliefs, making it a unique step forward in astronomy. What made Brahe's work especially remarkable was his dedication to precise observation. Unlike many astronomers of his time, who only observed planets at certain points in their orbits, Brahe tracked the entire visible orbit of each planet. This approach led to the most precise measurements anyone had ever made, data so accurate that later astronomers like Johannes Kepler used it to refine our understanding of planetary motions.
So let's proceed to Tycho's model of solar system. He established a theoretical model of the solar system known to us nowadays as Tychonic system or Tychonician model of the solar system. It is the idea of the heliocentrism and geocentrism, where combined where the Earth was the center of the universe while the other planets within the solar system revolved around the Sun. In 1575, Brahe built an enormous observatory in an island offered to him by King Frederick II, where he kept meticulous observation of the heavens. While most astronomers only focus on observing heavenly bodies at specific, unusual points in their orbits, Brahe intently tracked them in their entire visible orbit across the sky, creating the most precise observations made at the time. Brahe was extremely limited in his view of the universe, and his observation relied on what he could see with the naked eye. However, Brahe was able to construct instruments which aided this observation, and that is armillary spheres, also known as spherical astrolabe, were able to physically represent a model of the sky, enabling him to develop celestial maps of planetary movement. He made the most accurate measurements of planetary precision, which is especially admirable given that it was made before the advent of the telescope. It's an old tool that people use to study the sky and understand how stars and planets moves. Think of it as a 3D model of the sky. In short, the armillary sphere is a tool that helps people model the sky and understand how celestial objects move. In order to help prove that geocentrism was correct, Brahe extended an offer to German astronomer Johannes Kepler to join him in his island. This offer may have cost Brahe his life.
In 1572, Brahe observed a new star commonly known as the supernova. This supernova is brighter than any star or planet in the space that time. The Tycho supernova is classified as type 1A. This is a violent explosion occurs when a white dwarf star in a binary system pulls a material of its companion star until it reaches a mass limit or when the two white dwarfs merges. He also coined the term nova that came from the new Latin word novus, which means new.
Johannes Kepler, 1571 to 1630. Johannes Kepler was born in 1571 in Germany. He initially studied to become a Lutheran minister at the University of Tübingen, but due to his intelligence, he earned a scholarship to study. Later, he became a math teacher in Graz, where he wrote his first major book, Mysterium Cosmographicum. In this book, he defended the idea of the heliocentric model proposed by Copernicus, which stated that the Sun, not the Earth, is the center of the solar system. This idea went against the common belief at the time that the Earth was at the center. In 1600, Kepler became an assistant to the famous astronomer Tycho Brahe. Tycho had collected very accurate data about the position of the planets, and Kepler was assigned the task of understanding the orbit of Mars. Kepler's work on Mars revealed that planets don't move in perfect circle as was commonly believed. Instead, he discovered that planets move in elliptical orbits. From this, he formulated his real law of planetary motion, which completely changed how we understand the movement of planets in our solar system.
So let's talk about the three laws of planetary motion. The first law is the law of ellipse. All planets move about the sun in elliptical orbits, when the center of the sun being located at one focus. The sun here is not the center of the ellipse, but instead there is one focus. The planet then follows the ellipse in its orbit which means that the Earth-Sun distance is constantly changing as the planet goes around its orbit. This law just explains po the shape of the planetary orbits po around the Sun. The second law is the law of equal areas. This law states that the imaginary line joining the planets to the Sun sweeps out equal areas in equal time as the planet travels around the ellipse. So this law just explains the speed of the planetary objects around its orbits. So there is actually a term po dito. So the first one is the perihelion. So the perihelion naman is just the point where the planets are near to the sun, which means they move faster around their orbit. And the second one is the aphelion, which means pagka malayo po yung planets around the sun, mas mabagal po yung ikot nito around its orbit.
After the law of equal areas, we will now proceed to the Kepler's third law of motion, which is the law of harmonies. The law of harmonies states that there is a relationship between the time a planet takes to complete its orbit around the Sun and its average distance from the Sun. Or in other words, may relationship po yung layo or yung oras ng pagkumpleto ng isang planeta sa kanyang orbit depende sa layo nito sa araw. Like for example po is Earth and Venus. We all know that Venus is much closer to the Sun compared to Earth. Earth has an average distance of around 93 million miles to orbit the Sun, which indicates that Earth needed 365 days to complete its orbit. And on the other hand, Venus, it only has 67 million miles average distance from the Sun, which means kinakailangan po nito ng 225 Earth days to complete its orbit. To further understand this, let's proceed to the computation of the distance between planet and the Sun and the time needed to complete its orbit. So, to further understand the third law of planetary motion of Kepler, or the law of Archimedes, here is an example. It takes 0.615 years for a planet Venus to revolve around the Sun. Determine the average distance of Venus from the Sun. So, ang una po natin gagawin is, ilista po muna natin yung given, which is 0.615. It will serve as our T on our equation, which is the number of years kung gaano katagal na revolve po yung Venus sa Sun. So, and ang nawawala po is the average distance or the R cube. To find our R cube, here is the equation po. P squared is over R cube is equals to constant, which is the constant is equivalent to 1 year squared over astronomical unit cube. Para mahanap po natin yung R cube, ilalabas po natin siya dun sa equation. Magiging ganito po. R cube is equivalent to the square root of P squared over constant. Kaya po nagkaroon ng square root dito para po ma-cancel natin yung square. So, ang magiging itsura po na equation natin is R cube is equals to P squared over constant. Pero meron pa rin po tayong cube, which is kailangan po natin siyang malipat sa kabilang side. Kaya po ang gagawin po natin is maglalagay din po tayo ng cube na square root. So, ito-plug na po natin yung ating mga variables. R is equivalent to cube of 0.615 years all over ating constant na 1 year squared over astronomical unit cube. I-plug lang po natin ito sa ating calculator and makukuha po natin ang sagot na 0.72 astronomical units, which is, ito po yung magiging average distance or yung layo ng Venus sa Sun para na nangailangan ng 0.615 year para makapag-revolve around the Sun.